Hello students. Today we will discuss about free particle in 1D infinite potential well. In quantum mechanics, we know that the wave function carries all the information about the motion of the system. We can obtain the wave function by solving Schrodinger equation and the independent Schrodinger equation for one dimension motion reads as this. So the first part is the kinetic energy part, this is the potential energy part, and this is the total energy. So here E is the total energy and psi x is the wave function. Let us consider the problem for today, which is free particle in 1D infinite potential well. So the particle is free inside this. So if I consider this is one dimension potential well, where the sides the potential is infinite and the particle is free inside. So inside this box my potential is 0. So the particle behaves like a free particle, and outside the box I can consider that potential is infinite. Now this is the time independent Schrodinger equation, and outside the well, so for the outside the well I have x is less than 0, so in this side, and x greater than L, so in this side. So in this side potential is infinite. So if the potential is infinite in this region, to have one finite term here, I should have psi 0 outside. So for to have one finite term, so Vx is infinite outside the world. So here to have one finite term, since V is infinite, I should have psi x is equal to 0. So outside the world my wave function is 0. Now what do I mean by wave function is 0? If wave function is 0, the probability of finding the particle is also 0. So I can't find the particle outside the well. That means for one dimensional infinite potential well, the particle can't come outside the well. That's why psi x is 0 outside the well. Now let's see what happened inside the well. That means in this region. In this region means in this region where the particle is absolutely free. Now in this region, so I said V equal to 0. So time independent Schrodinger equation becomes this, and if I rearrange this, I get this, where this is the energy. And I'll consider this term as k square, where k square is equal to 2me by h square. So again, if I rearrange this, I found that E is equal to h square k square by 2m. Now this is the energy and wave vector relation for one free particle. Now when I have a free particle, there is no bound on this k vector. So if there is no bound on the k vector, E is also continuous. So the free particle, E is always continuous. Now let's see for this case where the particle is free only inside the well. However, it can't come outside, so it is bound inside the well. Now let's see what happens in this case to the energy of the particle. Now general solution of this is this one. This you can find using simple math, or I can use this solution where this C1, C2 are constant. K is the wave vector. Now psi x is equal to C1 sin kx, C2 cos kx, or C1, C2 and k is still unknown to me, and I have to find it out. To find it out, I'll use the boundary condition. So what do I mean by the boundary condition? The boundary condition is the condition which the wave function must satisfy. So for this case, since the particle can't come outside the well, at x equal to 0 I should have psi equal to 0, at x equal to L also my psi should be 0. So these are called the boundary condition, and this is the boundary condition for this given problem. Now if I use the first boundary condition, that is at x equal to 0 psi is 0. So if I put in this equation x equal to 0, so psi is 0, so my left hand side is 0. Now sine 0 is equal to 0, so this is also 0, but the second term, so cos 0 is 1, so this term is not 0. So to match the left hand side and right hand side, I must equate C2 equal to 0. So to match the condition 1, we should have C2 equal to 0. So now the generalized wave function becomes C1 sine kx. Now I have two more unknown variables, one is C1 and another is k. Now if I use the second condition, that means at x equal to 0, at x equal to L, psi is 0, then this side will become sine kl. So this is true only when sine kl is 0. Now sine kl is 0 only when kl will have values is equal to n pi. So kn can have value n pi by L. See, I have discussed this one before. For one free particle which is absolutely free, k is continuous. However, here k is not continuous. K can have certain set of value, or n is one integers. So the allowed values of k are pi by L, 2 pi by L, 3 pi by L. Now one can ask, why n not equal to 0? For that one also this condition is satisfied. But if I put n equal to 0, my k will become 0, and if my k becomes 0, psi will ultimately remain 0. So I should not take n equal to 0. So these are my allowed k values, and so these are the values. Now, so here as I discussed, the k values are not continuous, but they are quantized, because they have the kn has certain sets of value, and if kn is quantized, following this I get En equal to this. So my energy values for this given problem, or the particle is free only in an infinite potential well, is also quantized. So energy is quantized for this is also quantized for this problem, and this is the flavor of quantum mechanics. That's all for today. We'll meet in our next class. Thank you.